much. This seems like a wonderful event already. I'm very excited to be here today. So today, we're going to talk about AI. And we have three primary goals to get through by the end of this talk. First is let's define artificial intelligence, if that's even possible. Going to try to cut through a lot of the hype and other words I'm not allowed to say here. We will disambiguate the terms between different fields, because you're going to hear so many different technical terms, and oftentimes they overlap. And all that does is sow confusion and make it harder for people to know what they're doing. And for fun, we'll see some code, because it's always great to get to see a little bit of code. It's always fun, at least for me, it's a fun time. So let's start with a little story first. It takes place in 2010. I went to a lot of events, and people always asked a similar question. So, what do you do? Introduction to conversation. And 2010, I wanted to sound sophisticated, so I said, machine learning. I thought that sounded really cool, that it showed gravitas. I was serious, it was real stuff. And they would respond, what's that? They had no clue what machine learning was. So, about 20 minutes go by, and I decide, the conversations keep happening, so I decide to change my tactics. They said, what do you do? I responded, data science. And they go, I need a data scientist. They got really excited, and I collected so many business cards. And this was a recurring theme at every event I went to. It was the same thing, but different words. I didn't change anything, but they heard it differently. So now we fast forward to 2019, and I'm still going to these same events. And the same conversations keep happening. What do you do? So now I say AI. And people go, oh my God, yes. Maybe not that animated, but they love hearing AI. It's amazing. And I get a bill more when I say it's AI. It's the same thing, but different words. I haven't changed anything I do. And I think this is summed up very nicely in this tweet. Everyone knows the 10-year challenge that was going around? Andy posted this. The same exact equation, linear regression. It was called statistics. Now it's called machine learning. We've been doing this for 100 years. Sure, we could do it bigger now, bigger data, faster, but it's more or less the same thing with different words. By now, I'm sure we've all seen this Venn diagram. It's part of data science bingo. It needs to be seen at least once at every data science conference, so you're welcome. All the other speakers can change their slides. You don't need it anymore. But everywhere sees this. We all know it's about the hacking skills, the math knowledge, the domain expertise. We've all seen this. But there's a new Venn diagram making the rounds now. The AI Venn diagram. Now this is from the book Deep Learning. It's just deep learning. And it's an amazing book. If you ever want to learn the concepts of deep learning, it not only is it informative, it's well written. They have this diagram in here. They say AI is the field. And it's about knowledge. And machine learning makes up one part of AI, according to the way they represent this. And within machine learning is deep learning. Now, of course, this is contentious, because some people say, what, there's other machine learning besides deep learning? I never heard of such a thing. And there's people who think it's just another tool. So, of course, there's a lot of different definitions going around. So, let's try to define AI. Let's see if we could say what it actually means. So I saw this tweet, which I thought described it very well. When you're fundraising, it's AI. When you're hiring, it's ML. When you're implementing, it's linear regression. When you're debugging, it's printf. Of course, there's some linguistic implications here, and I do believe this is a lot of the hype. I saw an advertisement in San Francisco. It said, 5G, blockchain, AI. Yeah, and I saw it all over the place. So, well, that was fun. I think we should try again. That was a fun definition, but I think we can get a little more at this. And I was speaking on a panel about 2 years ago about AI when it was just starting to bubble up a little bit again. And we came across this great definition on the panel, and I really liked it. It's what humans find easy, but computers find hard. Now, this is very broad, and of course it changes over time. But so has our definition of artificial intelligence. The cutting edge of AI used to be beating humans at chess. That was hard to do. But ever since taking down Kasparov, you can find AI in any app that plays chess for you, and it could beat most of the players playing it. It's been done. So now, well, until recently, the cutting edge was beating humans at Go. But humans lost that battle last year. The definition of AI is fluid in this sense of it's what computers find hard. Because now we're moving on to beating humans at video games. The common thing I just said all there is beating humans. It seems that AI is just trying to be better than humans at things, to beat humans. So of course that's got the government regulators interested. Governments are trying to get involved now. They want to regulate AI. But do they really know what AI means? What are they regulating? Are they regulating a robotic machine in a car factory? Or are they regulating online advertising? And I was at a AI dinner in Washington, D.C. last year, and someone said something that really struck with me, and I'm really happy he said it, because all the lawmakers in the room were getting a little excited. And he said that people want to regulate AI, but no one cared when it was called logistic regression. AI is scary. People get worked up about it. It's this thing out of science fiction. Statistics is not scary, at least not in that way. Lots of undergrads have been scared by it, but no one's worried about it taking over the world. Which again brings us to this tweet. We're doing the same thing we've always been doing. The words change. It's just the marketing has changed, and the marketing has people up in arms. Because it's still the same thing with different words. So let's go ahead and examine some of those words. Let's start with the motivation for that tweet, linear regression. It's simple. This is the foundational learner. Whether it's statistical learning, machine learning, data science, statistics, regression is the baseline. And I'm sure most people in this room all know the equation for regression, y equals a plus bx, right? It's slope-intercept form from middle school. You didn't realize it in middle school, but you were doing machine learning and AI. Let's talk about that A. Traditionally, it was called an intercept, but now they're calling it a bias, which I can sort of see because the curve is shifted up or down. But bias traditionally has a completely different meaning involving the bias variance trade-off, and they're reusing a word without ever saying what happened to the old word. Or newcomers, they come across two different words now, and that's dangerous. Then the B. That's literally the slope of the line in terms of geometry. Well, growing up, not quite growing up, but growing up professionally, I called it a coefficient, but now it's called a weight. And weight kind of makes sense, I get that, because it's like, how much does this variable weigh? When you talk to clients, like, oh, what are the weights? And I get that. The problem is, traditional methods, the weights were how valued each row was. And all of a sudden, it's no longer the rows, it's the columns. And no one's bothered looking at the old literature. And that is very problematic. Especially when you have a newcomer learning from two different sources. And they're like, wait, what's going on? So let's look at this curve. It's a binary scaling curve. It takes any number and transforms it between 0 and 1. It's represented by this equation, 1 over 1 plus e to the negative x, also known as e to the x over e to the x plus 1. Right? A little bit of algebra, you can write it either way you want. And we've been using this for logistic regression for decades. And you might come across two different words for it. It's either the inverse logit or a sigmoid, depending what field you're learning from. It's almost as if the people in these two fields didn't bother reading the papers from the other fields. But I do ask, seriously though, which one is less informative? What is a logit? I want to put, most people don't know what a logit, most people in this room probably do. Most humans don't know what a logit is, nor a sigmoid, so neither one's particularly helpful. So let's see what happens when you get new data, and you want to make use of it. You want to get a point estimate from some outcome variable on this new data. You're saying y hat, your point estimate, is equal to some estimated function of your new data. Simple, easy. You're scoring information, which by itself is a newish term. I always called it prediction, but now it's inference. And this is maddening, because in traditional statistics, inference meant understanding and explaining, and it was always antithesis to prediction. Maybe not antithesis, but it was orthogonal at least. And all of a sudden, inference means predictions? And the first time I heard a tech company I was vetting for a VC, they said, well, at inference time, I'm like, inference, you're doing predictions. And I realized they read completely different papers. And that can really screw up someone trying to get used to this. It's not fair to people. Using talking about the same thing with different words is very difficult on people. So hopefully we can clear up some confusion about all of these terms. You don't want people to feel lost. I know we have a lot of educators here, so it's important when you're teaching, say everything. So now when I teach my class, I let them know up front all the different words that could be used. Maybe not all the words, but a lot of the words that could be used for their purposes. This way they don't get scared of things. It's very important when teaching. So now that we have looked at what we're going to call AI, and we've talked about some of the different terminology, it's time for some code. I'm going to use R. That's my tool of choice. Anyone who knows me knows I'm a little obsessed with this language, almost as much as I'm obsessed with pizza. And I love combining the two of them. That's the greatest thing. And R has been used for machine learning for decades. So we're going to start off by looking at what is perhaps the most common type of AI you're going to come across. An if-else statement. You'd be surprised how much this solves, and it looks like magic to people who didn't code it. Now in this case, if else, price is greater than 100, sell, otherwise buy. And I think we're all being honest in this room, this solves so much. It's a rule-based system. And remember, back in the 80s and 90s, rule-based systems were the cutting edge. Expert learner systems, you would sit down with a professional in the field and they'd go over every possible logical scenario and you'd code rules. That was cutting edge. And still to this day, this solves a lot. But you're not here for that. You want something that's more advanced. Right? I think you'd all be disappointed if we just had an if-else statement. Or maybe vindicated. So we are going to turn our attention to logistic regression. This is our inverse logit, or sigmoid, if you will. And technically, it should be called binary regression, because logistic regression is just a special case of binary regression. But it's 99% of the binary regression is logistic, so let's call it that. And we are going to do a two-class classification. And now all of a sudden that sounds cooler and hotter right now. Classification is so much cooler. That's machine learning. Logistic regression, that's for those nerds back in the stats department. So we're going to do a two-class classification, and in particular, we're going to do a penalized logistic regression. Machine learning is really just optimization. You're trying to minimize or maximize some expression. In our case, we have the loss function on the left. It's your standard OLS, well, generalized OLS, plus the penalty term on the right with that lambda. And the penalty term helps you work with larger data sets with too many variables. It helps you get more stable predictions. It lets you do variable selection. And there's lots of tools to do this. And probably the most prominent is GlimNet, the elastic net. But we're going to use it indirectly. So first, though, we have to prepare our data. We all know that preparing the data takes 80% of the work, and the other 20% of the time is spent complaining about preparing the data. That's a key part of the process. You must complain about it. So luckily, once you've done all the data munging and all that, the preparations for your model are kind of easy now thanks to the recipes package. The recipes package allows us to specify different steps to take to define how our model is going to look. In R, we've used the formula interface for a long time, and it was great. It was an amazing interface. But now we can do things even more programmatically thanks to the recipes package. And you basically start with a general formula, credit tilde dot. We use credit on all the other variables. Then we do a step other. We take the categorical variables and collapse the uncommon categories into an other category. We get rid of any variables that have zero variance because they don't help us at all. We center and scale the numeric variables so they're all on the same footing, because that's important for penalized regression. We turn the categorical variables into dummies. We add an intercept for good measure because it helps with mathematical stability and maybe interpretation sometimes if you care about interpretation these days. And then we prep it. The prepping function calculates everything. It calculates the mean, the standard deviations of all the columns. It calculates what columns need to be factors and what the factor levels are. Once you've prepped it and done the calculations, you can juice your data and get your prepared data set. And yes, the recipes package has functions called prep, juice, and bake. We love puns in the R community. So now that we have our model and our data defined, let's go ahead and define the model. We could go ahead and use the functions directly, but there's a new package called Parsnip, which makes it so much easier. And yes, we have gone from the caret package to the Parsnip package. They love puns. So we are going to do a logistic regression. And that's very easy with Parsnip. You declare you're doing a logistic regression right here in this phase, and we are going to set the engine to be GlimNet. We are going to use GlimNet to run our logistic regression. You then feed that into the fit function, and you provide a superficial formula because your data's been all prepped. You have just your outcome and then everything else. There's no other variables left anymore. And you provide that prepped data. You run this, you run your model. And with GlimNet, there's that penalty. The question is, how much penalty are you doing? So you fit, instead of one model, you're actually fitting about 100 models. And you get a result that can be visualized this way with a coefficient path. Each line represents one coefficient for one of the variables, and categorical variables can have more than one coefficient because there's different levels. Each line represents a coefficient, and these are the paths. As you go from left to right, you're going from less penalty to more penalty. And each vertical point, if you draw a line vertically, that is one realization of the model. That is one possible evaluation of it based on the level of penalty. You can see as you increase the penalty, the coefficients get smaller. They get dragged towards zero. It's like a Bayesian prior. And depending what level of penalty you get can greatly affect your model. If you choose very little penalty, a small lambda, you get a lot of variables still in the model and very big coefficients. So many, in fact, you can see the graph has an overplotting issue. The y-axis, the column names are smushed together because there's just so many, and only so many fit on the screen. Or you can choose a bigger penalty and get a still somewhat complex model, but a little simpler than before. It fits a little better now. The coefficients are smaller, and there's fewer of them. We've done variable selection. Or you can choose an even bigger penalty and get a really simple model. It's only a handful of variables are left now. And somewhere in there, you might have been overfitting, you might be underfitting, you might be just right. And that lambda was a hyperparameter. A parameter are the actual coefficients, or the weights, if you will, whereas the penalty amount is a hyperparameter, something you can control. Another hyperparameter for penalized regression is the mixture parameter, seen up here. All you need to do is take the same code and add an argument, mixture equals 0. Before we were doing the lasso regression, which is L1, by setting mixture equals 0, we're doing L2, the ridge regression. And when you do that, you get a completely different realization of the model. Recall before the curves went straight, then dived towards 0 sharply. Now they're asymptotically going towards 0 very smoothly. Different. Not saying one's right, one's wrong. They're different. And depending on your combination of hyperparameters, you're going to get different results. One's not necessarily right, but one might be better. So half of machine learning is just brute forcing your way through hyperparameters. You're just turning different knobs and seeing which ones give the best results. And typically the best results is defined by predictive power. You'll use a validation data set or cross-validation, and it'll say which one gives the best predictive power. So tuning the knobs is something that can easily be done. Lots of software that can do that. So now we're going to look at different engines we could use to fit that same model. GlimNet's not the only game in town. We could do GLM. GLM is just a simple generalized linear model. It's been fitting logistic regression for a long time. All we had to do in this code here was change the engine from GlimNet to GLM, and it did all the work for us. We didn't need to learn a different interface. It doesn't do penalization, but you get confidence intervals. And some people still want those. They're really good to have, and it's kind of a shame they've been lost in the battle to get the best predictions. You can also use, by simply changing the engine, stan. All we did was say set engine stan, and now we get a full Bayesian MCMC. We got our confidence intervals back, and we can still perform shrinkage and penalization. And we can make great inferences now thanks to the engine being stan. It's a pre-built stan model that takes care of all this for us. It's really nice. Let's say your data is really, really large, and you've already put it on a cluster because you've already paid for Spark. Well, you could set the engine to Spark, and it will now use Spark MLlib to fit your penalized logistic regression, so you don't need to spend the I/O time getting your data in and out of Spark. And let's say you want to be cool, you can do Keras. All you need to do is, once again, set engine to Keras, and it will fit a single layer perceptron to fit your data. And Keras will do all the work in the back end for you. Deep learning can be simple. No one said it needed to be complicated. And if it's a one-layer perceptron, you can extract the coefficients and do what I'll call inference, but explanation on them. The results may or may not be better than a regular regression, but you can do it. Or if you want to get complicated, you can go full-on deep and fit an entirely deep learning model using the Keras package in R. We're starting with a dense layer with 512 hidden units. We are using a ReLU activation because those are determined to be good activation functions. We'll then do a layer of a round of batch normalization and a round of dropout to help with overfitting. They'll do another deep layer and another dropout and batch normalization, then another one, because we can. We could do more, but it won't fit on the slide, so we'll just do 3 layers. And at the very end, your output activation function is a sigmoid, because that's what we're calling logistic regression now, a sigmoid. And this will fit you a model. We just saw 6 different ways to do the same thing, but using different words. They all accomplish the same goal, a logistic classification. But in case that wasn't enough, let's see something different. But the same idea. We are still going to do classification, this time with decision trees. And decision tree is essentially a nonlinear regression. And it's that nonlinearity which lets you capture so much. Because linearity was invented as an assumption to simplify the math before we had computers. Now we have computers, we can understand and acknowledge the real world isn't always linear. So we can do nonlinearity. And by the way, I've taken to calling deep learning extreme nonlinear modeling. Because it's essentially what it is. It's the nonlinear activation functions that give it the power. Without there, it's just linear. So let's do classification with decision trees. We once again turn to Parsnip. And we've only changed 2 lines here. We've said that we're using a decision tree and we're specifying mode equals classification to be explicit. And we're using the RPart engine, recursive partitioning, which has been in R for decades. And we fit a model. Without doing much effort, we changed a little bit of code. And we can now visualize our decision tree like this, using rpart.plot. And we can see here, it walks you down your decision path. It shows you the different questions you would ask to get to your answer at the very end. That's why it's called a decision tree, because it's really partitioning. We call it a partition tree because the outcome looks like a decision tree from decision management. And it's nice, it makes good predictions, it's understandable, you can interpret it fairly easily. As it gets more complex, it's hard to interpret. But it can have high variance, which we'll get to. So that was our part. Let's see some more of the same. You can, instead of using rpart, use C5, which is a very popular partitioning algorithm for fitting decision trees. All we did was change the engine. You can also use Spark again. Just in case your data is already in Spark, you can use it, which is the only reason to use it if it's already there. All we did again was set the engine. Look how awesome this is, how easy this is. Now, the problem I mentioned with decision trees is they're high variance. You change your data a little bit, you can get a completely different model. One of the earliest solutions for that was a random forest, which I'm sure most people here know. You fit 1,000 trees, each one randomly grown at each step of the way, and a forest makes a better prediction. But that's been superseded. So let's do what we've been doing, but with boosting now. Boosting is a way for a model to learn from its previous iterations and get better each time. You're boosting its performance. It's more technical than that, but each time it's learning from how well it did on the previous round of performance. Not only does it give better predictions than a single tree, it's more stable. It's more applicable. It's less variance. It's less variable. So switching our model to a boosted tree is quite easy. We use Parsnip again. We say we're doing a boosted tree, and we set the engine to XGBoost. This whole time it's been pretty much the same 3 lines of code with slightly different names. XGBoost is probably the leading way to do boosted trees. And after you've boosted the tree, since you're fitting a few 100,000 trees, you can get a variable importance plot, which is really nice. It tells you how important the variables were. It doesn't tell you what they're doing. It doesn't tell you their effect. It tells you their importance, which is a key distinction here. It's how much it impacts the outcome variable, not which direction it's going. I can't tell you if it's a negative impact, a positive impact, or its magnitude. That tells you how important it is. And there are other ways to boost. And there's a few of them we can get to in Parsnip. One of them is C5. Once again, you just simply set the engine and C5 comes to our rescue again. And of course, Spark. Spark has a nice machine learning library. There are other methods not implemented in Parsnip yet, like GBM, which was created by the creators of boosting. And there's a few new boosting trees out there, like GBM from Microsoft and CatBoost from Yandex. And they're both supposed to have really nice performance. So we have seen many ways to accomplish our goal here. In this particular case, our goal was classification. And we saw linear methods, or more specifically generalized linear methods. We saw tree methods, we saw boosting methods, and we saw a deep neural network. All doing the same thing. So it's very important to remember here, with all this stuff we can do, your AI code can be complex or it can be simple. Sometimes simple is better. In statistics machine learning, there's something called the rule of parsimony. When two models are almost equally performant, you go with the simpler one. And all these things we've been doing today are all just the same thing with different words. So the next time you're at a party and asks, what do? You'll now have many answers. So thank you very much. I think inference, traditional inference, explaining things is very important. You go to a client, they always want to know what's going on. And you always have to tell them there's a trade-off between prediction and explanation. Which, while that's always going to be true, because if you have a nonlinear function, you can't just say, if x increases, y is going to increase. That doesn't mean you can't try to explain things, though. And there is progress being made. There's a piece of software called Line, which lets you go through and try to figure out what each row is contributing, how it's affecting things. And people are trying to reconcile them, but there is a heavy culture of just squeeze all the predictive power you have out of it. So you got to change the mindset a little bit, because there are people doing great work trying to explain. They sort of got to all get along, and getting along doesn't always happen in these fields. But if they do, then you might be able to marry the two. There will always be that trade-off, but you can get closer to understanding at least what's happening. And they're going to get there. They will. Different perspectives are amazing, but just sometimes you read this stuff and it looks like they didn't even look at the other literature that's been out there for decades, and they're reinventing the wheel sometimes. And when they're completely different fields, like when physics comes at it from one point of view and math from another point of view, they are completely different fields. But I've seen a lot where the fields were adjacent to each other, and it's very clear they didn't talk to each other at all. And I think it'd be great if when they're like, look at this new thing I invented, you just sort of look, oh, someone invented it 20 years ago. And even if that's going to happen, it's still the newcomers, or even maybe not even the newcomers, but someone new to each field. It'd be really great if there's some sort of dictionary to disambiguate, because different words causes conflict. It's sort of like, it'd be nice if there's a universal language in the world, but then you lose the beauty of French and of Thai or whatever language is. But if everyone can communicate together, things could progress better. So different perspectives, yes, absolutely. I'd like to get the terminology simplified.
So we need emojis for data science.
If you ever follow Twitter and it's talking about R, it's all emoji.